Welcome to my channel. My name is Opubo. For those of you new to the channel, I say to you, welcome. And for those of you returning, I bid you welcome back. Good to have you return. You're all well appreciated. As usual, in this channel, I present various ideas and designs of technologies, mostly from the Technology IP Bank of Enhanced Knowledge LLC, often integrated from several other technologies already within the bank and made ready for adoption by the Adoption Brokerage Division. This presentation is on amino acid process technology with respect to conservation economy, and it focuses on the production of amino acids being foundational biologic for good health and wellness for the citizens of the conservation economy from the technological perspective, and the approaches such a community or region or even a nation could adopt to ensure the sustaining of a conservation economy. Amino acids are the biologics of life being produced by anabolic reactions of the metabolism and used in the production of protein during biosynthesis. The reactants for the production of amino acids, of course, includes carboxylic acids, which may or may not be produced or may not be consumed from external sources. The provisioning of amino acids directly to the cells, therefore, implies that the cells are aided in leapfrogging the anabolic reactions process, and therefore growth accelerates. In fact, this is the reason for muscles growth with people who consume steroids, which is produced with amino acids. Amino acids, therefore, are necessary for life, and the production of this biochemical or biologic from the utilization of endemic raw materials would be very enabling of conservation economy. Then, of course, carbolic acids, the reactants for amino acid, is produced with a conservation economy technology, making amino acids derivative of conservation economy, and therefore, and hence, enabler of such. Digressing for a moment, however, before delving into the process technology for amino acids production. If you have not as yet subscribed to the channel, I implore you to do so, please. Click the subscribe button now. Go ahead now and subscribe by simply clicking on the subscribe button below. The subscription would cause the system to keep you informed by notification of the next presentation the moment one is published. And also, of course, help me to more consistently continue to elicit the peace dividend of conservation economy. Now, back to the presentation. Generally, the production of amino acid has been mostly by two methods. The microbial process, by which microbes are enabled, fed specific nutrients such that they produce amino acids, and the amino acids are extracted from them. And the other approach is the degradation of proteins by hydrolysis that enable extraction of the amino acids from the protein as also a method. The extraction of protein is obvious, as amino acids are used to produce proteins. An effective approach, though, is the combination of the microbial production of amino acids and the protein decomposition approaches. By this method, microorganisms are utilized to decompose biowaste, which naturally contain proteins, and in the process release the amino acids of the proteins in the biowaste. In this regard, food waste is a reliable source of amino acid, as are domestic biodiscards. However, the use of food leftovers for source as opposed to the provisioning of the food to human beings who need food adversely impacts humanity to a great extent when the world is struggling over hunger. Microorganisms readily convert carboxylic acids into keto-acids, which are then utilized to produce amino acids. So this option circumvents the need for use of food leftovers. So then the production of amino acids by microorganisms specifically fed with carboxylic acids prefers the most efficacious approach. After all, the carbon capture is not a direct form of food for humans. And the microorganisms are not fed carboxylic acids. The microbial process of amino acid production is shortened with the result of potentially high productivity. On the basis of this reasoning, one such design in the Technology IP Bank, the technology of this presentation, has been integrated such as to be driven by the utilization of carboxylic acid as reactant feed to microorganisms to produce amino acids. And the process technology is as shown in the figure. Conceptually, this technology extracts the first two of the four reactions of anaerobic reactions and effects then towards the extraction of the amino acids of the biodiscards of domestic products. The biodiscards, domestic biodiscards, or biotic resource, together with carboxylic acid, is fed to microorganisms which decompose the protein of the biotic resource, letting free the amino acids in the process, but also utilizing the carboxylic acids to produce keto-acids that subsequently get converted into amino acids. By design, the technology consists of two biotic resource processors, hydrolysis anaerobic bioreactor, microbial decomposition anaerobic bioreactor, two or more amino acid separation process unit operations, two storage tanks holding carboxylic acids, and extraction organic oil, a storage tank for selecting the amino acids, and three sanitizer reactors, and ultimately, as always, a controller system for the purposes of keeping the fluctuations of the system within a very narrow band. During operation, the biotic resource is pumped into the father of the two leftmost equipment, where the resource is processed into a microparticle-sized mixture and then pumped into the nearer equipment, a sanitizer bioreactor, where the biotic resource is sanitized to deactivate all the microbes. The sanitized resource is then pumped into the hydrolysis anaerobic bioreactor, which is also simultaneously fed with carboxylic acid, water, and the microorganisms specifically chosen for the hydrolysis. The output of the hydrolysis anaerobic bioreactor flows into the sanitizer bioreactor just ahead of it. That again deactivates the microbes of the hydrolysis anaerobic bioreactors, carried out over before being pumped into the microbial decomposition anaerobic bioreactor, which is also fed again with carboxylic acids and the use-specific microorganism, a species of myxobacteria, which consume the dead hydrolysis microbe cells, effectively exposing the amino acids produced in them from the consumption of carboxylic acid. The output of the microbe decomposition anaerobic bioreactor is pumped yet again into a pairing sanitizer bioreactor, again just ahead of it, for the deactivation of the myxobacteria, after which the mixture is then pumped into the first equipment of the liquid-liquid amino acid extraction sequence equipment series, with the final outflow from the series being pumped into the storage tank designated for the storing of the amino acids. By the trace of the progression of the bioprocess so far, there can be uniform acceptance that at this time, there is, in fact, a conservation economy technology that enables large-scale production of amino acids for use in every other conservation economy technology that requires amino acid as a reactant or co-reactant. The materials of construction of the process equipment being mostly Still, the process technology is well suited for the utilization of discarded process equipment of process companies that have shuttered in every region, allowing for the elimination from reuse of such equipment that would otherwise be branded waste. So, under the requirements of conservation economy, this technology has a significant role of service. Now then, if interested in licensing this technology, please send an email to me. The email address is put in the pinned link below as are other useful information. Regarding licensing consideration, there are some notes that should be of interest though. The charging of the reaction mixture with carboxylic acid requires providing a source for carboxylic acid, meaning this technology may have to be co-licensed with a carboxylic acids process technology. Of course, that requirement quickly expands the licensing scope, as the carboxylic acid process technology requires the co-licensing of one of the two carbon capture technologies. Worthy of note that while the process as presented displays only one of each type of equipment, the actual industrial adoption may require more than one, as required by the production volume specification. And this is significant because the technology license agreement generally is based on per equipment and then aggregated before the functionality clause is added. Further, the technology as presented is also sort of truncated, with the domestic biodiscards receiving operations omitted. Also, the final process of separating the amino acids from the extracting organic oil is also omitted. The addition of both in the technology for licensing will significantly increase the licensing and adoption expenses. The infrastructure of the controller system is also of consideration, as the mirror equipment process controller technology that form the base technology often gets integrated into a very complex structure depending on the production needs. The several multi-phase liquid extraction equipment in the process suggests that the control server of each case would involve computation-intensive analysis, and as such possibly require the control server be adapted into supercomputing parallelism control server, and therefore add significantly to the licensing pricing as well. That said, I wrap up the presentation by saying to you, thank you for being here, and I appreciate your coming to listen and viewing the presentation. And if you have not subscribed yet, do please subscribe to the channel now. I do hope and expect that you would consider coming back for the rest of the future presentation of the varied technologies. The fact is, even if you do not adopt any of the technologies, some might just change your perspective of society and life. Until the next presentation, I wish you be well.